This is chapter number 34, Faraday's Law of Induction. The principle behind this chapter can be easily thought of as a modern physics principle that underlies this modern life. So let us first recall some of the Faraday's experiments. Faraday's experiments. So Faraday observed the following. He connected a loop of wire to an ammeter. This is an ammeter, and he connected it to a loop of wire. Faraday then moved a magnet towards the coil. He noticed that there was a deflection in the ammeter, meaning that a current was set up in this particular loop. He also observed that if the magnet was pushed towards the coil or away from the coil, as long as there was movement relative to the coil and the magnet, there was always a current set up. He further observed that if the magnet was stationary and the coil was moved towards or away from the magnet, there was a current set up in this particular coil. It didn't matter whether the magnet moved or the coil moved. As long as there was relative motion between the two, there was a current developed. He further did some more experiments in which instead of a magnet, he placed another coil. So this is the original coil, and in front of it, instead of a magnet, he placed a coil which was connected to a battery. And we all know that a current carrying coil produces a magnetic field. Faraday realized that as long as the current in this coil was changing with respect to time, that is, if the moment you switch it on, the current goes from 0 to a maximum value. As long as there was a change in the current in this particular coil, there was a current produced in the other coil. Similarly, if you switched off, the current went from a maximum value to a 0, there was a change in the current here. There was a current introduced in this particular coil. But he observed a very important thing. Just as when there was no relative motion, there was no current. Similarly, when there was no change in the current in this coil, there was no current introduced in this. So this was very puzzling. And to explain it, we need to introduce a concept called magnetic flux, which is very similar in spirit to electric flux. Let us introduce the concept called magnetic flux. Magnetic flux associated with any coil is given by, the symbol used is a capital Phi with a subscript B, is integral B dot dA. Recall, electric flux was given by phi subscript E dot dA. This was the electric flux. The equation in the box is the magnetic flux. The SI unit of magnetic flux, SI unit, is Weber, W-E-B-E-R. So therefore 1 Weber is equal to 1 Tesla into 1 meter square. So 1 Weber is Tesla meter square. Now how do we connect it up, connect the concept of a flux to the current? This is where the important contribution from Faraday kicks in. Faraday said, as long as there was a change in the flux associated with this coil, a current would be introduced, or rather a EMF would be introduced. So let me write it. The magnitude of the EMF generated in this coil is equal to the rate at which the magnetic flux changes. You can see, as long as the flux associated with this coil changes, there is a EMF. And how is the flux changing? As you move the magnet towards or away from the coil, the number of magnetic field lines passing through this particular coil keeps changing. If it keeps changing, there is an induced EMF. This is called induced EMF. The word induced is very illustrative here. It means that you're inducing something, you're forcing something to be done. So there is a EMF induced because of the fact that the flux associated with this coil is changing. Similarly here, as the current keeps changing with respect to time, the magnetic field is also a function of time. If the magnetic field is a function of time, the flux associated with this coil, because the definition is B, this also keeps changing with respect to time. If this changes with respect to time, flux also changes with respect to time. And Faraday has told us, if the flux changes with respect to time, then there is a induced EMF. This is a very interesting phenomenon. So you can ask the question, in how many different ways can I change the flux with respect to time? Let us look at this particular formula. Let us expand this. So therefore flux is nothing but B into A into cos theta. So if I want to change this with respect to time, then there are three different possibilities. You can change the magnetic field with respect to time. You can change the area of the coil with respect to time. Or you could change the angle with respect to time. And let us clarify, where does the angle come in? The angle comes in, if you remember your electric flux. Suppose there is a surface associated with this coil. Then if these are the magnetic field lines, then the angle, the normal dA vector, and this is B vector, this is the angle, theta. So therefore, if this angle also changes with respect to time, that is the angle between B and dA vector, then also the flux can change with respect to time. Now you are smart kids, you should be able to figure out which is the most easiest way to change the flux with respect to time. And we all know the modern alternating current changes this particular angle with respect to time. Changing the area, increasing and decreasing the area of a coil is very cumbersome. Similarly, generating time dependent magnetic fields is not a very practical way. So what you do is you keep the area of the area of the coil fixed. You also keep the magnetic field fixed, but you vary the coil in such a way with respect to time that you produce a EMF. So let us do that and see what happens. Flux, rate of change of flux is equal to BA d cos theta by dt, which is nothing but, so this angle has to change with respect to time. And let us go to something called the Lenzs law. Lenz's law is nothing but a restatement of the conservation principle. You could ask what is the direction of the current, and here I would like to tell that there is a very important distinction between the if a magnet is moving towards or away from the coil. If Faraday observed that the direction of the current, if you move this magnet towards the coil, is opposite to the direction of the current if you move this magnet away from the coil. And Lenz gave an explanation as to why this happens. Lenz's law tells us that the direction of the induced current, kindly note there is an induced EMF. This EMF will generate a current in this particular loop. The direction of this induced current is such that it opposes the change that produces it. What does this mean? It means that suppose let us say this magnet is pushed towards the coil. It means that the flux is increasing in this particular coil. If the flux is increasing in this coil, then the current is generated in such a way that it does not want the flux to increase it with respect to time. So therefore, it will try to oppose this particular increase in flux. So let me expound this using another example. Suppose you have a coil. So let's do this carefully. You have a coil and I am pushing a magnet towards the coil, and I ask what is the direction of the induced current. So Lenz's law tells that if this is the north pole moving towards the coil, then the current will try to oppose this, and the only way the coil can oppose this is if this coil, that is this face of the coil itself, behaves like a north pole, because we know north and north pole oppose each other. So if this has to behave like a north pole, the current has to be induced in this direction. As you can see, if the current is induced in this particular direction, then there will be magnetic field lines in this particular direction. I refer you to figure 34.5. Refer figure 34.5. Similarly, if we are trying to pull the magnet away from the coil, that is the flux is decreasing, then the coil will try to prevent this movement of the magnet in such a way that it tries to attract it. The only way it can attract it is by behaving like a south pole. So therefore the current direction will change.